Now, to start with, what we're going to do is we will summarize some of the results that we already have from modeling projectile motion. So here, what I've drawn is an object being projected at angle alpha to the ground. Okay, and last time what we found was, in fact, this object travels according to the, or let's put it this way, the path that this object takes is a parabola. And we found the equation for this parabola. It's one of the last things we did in the last lecture. Okay, so just a couple of points. So what happened was, well, we set up our reference system and we modeled the problem for an object. This is our object, which is solely exposed to the action of gravity. So in our case, we neglect air resistance, we neglect the effect of rotational motion from the Earth, and we assume that gravity is constant. So we have the action of the gravity force, and then we could use Newton's equations of motion to determine the velocity vector of the object. Okay, so this was this. And this was just from routine integration of the equation we derived from Newton's equation of motion. And then in addition, don't forget we had to use initial conditions, which embed the initial horizontal and vertical velocity given to the object. And then what we did was we did another integration and we ended up with the position vector. In this case, our object, where it's launched, coincides with where we chose our reference system. And in this case, this is the expression you would get for the initial condition where r is the zero vector. We also found the time, capital T, of which at which the max height is achieved. Okay, and this was found to be this. And we also derived an expression for the maximum height at that time, capital T, which was given by this expression. Don't forget also, it takes twice capital T for the object to return to the ground. And what we should be able to do now is use these expressions in anger to solve a couple of examples. Now, preferably, what I would like you to do is not memorize results. Okay, this is pointless because over time you will forget. The best thing to do to learn this theory is to understand how you derive the results. Okay, in fact, this is typically the best method to learn new things all the time in mathematics. Learn how things appear, how they're derived, and why they are. Okay, so I am going to, having said that, ignore this advice, but as we tackle the examples, but please keep this in mind, that you should be able to derive all these expressions given some information, such as this example. So this example is related to a football which is kicked and leaves the ground at a speed of 30 meters per second. And it's kicked it leaves the ground at an angle of 40 degrees. So we're asked to find the speed of the football after 2 seconds and the greatest height reached by the ball. So in this case, if you didn't know the formula, you'd have to model this problem from scratch, which again is the preferred method. However, now I'm just going to routinely use these results that we derived, because after all it was 1 hour's worth of a lecture. So we have a speed given to us, so that's our u, 30 meters per second, and we're given an angle with which it leaves the ground, so this is our alpha, and this is 40 degrees, but please keep in mind that calculus is built on the radian. So you do need to convert this into radians. And to do this, you just multiply 40 by 2 pi and divide by 360. And this will give you 2 pi over 9. Okay, so that's your angle in radians. You can use degrees if you're doing the calculation, but please remember to put your calculator in degrees, okay? Preferably, as we're mathematicians, we'll undoubtedly meet calculus, and radian is the preferred measure for angle. Okay, so this is an illustration of what we have. It's just a repeat. So here's the football, y, x, 0, there's the ground. Okay, 40 degrees. This is the speed u, which is 30 meters per second. And it's up to us now to use the results to find 1. Speed. Now remember, speed after 2 seconds. Remember that speed is magnitude of velocity vector. Therefore, what we should do is we should compute the velocity vector at 2 seconds and then compute the magnitude. All right, so this is what we're going to do. I'm going to copy and paste this result. Again, know how to derive these things. It is very useful and it will help you in the future as well if you ever encounter more mechanics in the program. So you have your velocity vector, which is this. Good. Our alpha, I'll just plug in the values. So we have 30 cos. Now, I'm going to put 2 pi over 9 plus. Now, what about g? Well, g is 9.81. Is our acceleration due to gravity. So 9.81 times, now, don't forget 2, because that's t equals 2. That's another important point. We want the velocity first, and then we can work out the rest. Plus 30 sine of 2 pi divided by 9. Okay, now, clearly I wrote angles in radians, so when I do my calculation, I will, of course, compute using the radian. So I'm just moving to the calculator. Let me just see. So, okay, I'm just entering in this information. Okay, so if you do this, what you should find is that you get the fair. Now I'm going to explain something here, and this is particularly useful with respect to some questions and assignments that you'll do in future. So I'm going to write this in like this. So the first component is 22.981, and the second component is minus 0.3, or at least I get it to this. And this is to 3 decimal places. Now, I simply, and this is meters per second, I simply truncated each component to 3 decimal places. What I actually want is, it's v, by the way, it's v when t is 2, is I want the modulus of v when t is 2. Now, here I truncated. Ultimately, when I truncate, I introduce an error. It's not an exact figure. Therefore, when you're doing these calculations and they involve subsequent steps like this one, for instance, I'm now going to compute the modulus now that I know this vector. But actually, what I'm doing in the background is my calculator is set to retain these components to full precision. Okay, so there is no truncation in my calculation at this step, but I simply truncated for a couple of reasons. To make the presentation of this more digestible and not cumbersome. So that means that I'm not spent writing out digits to the nth decimal place, and just to give you a feel for what you need to work towards when you compute the answer. So now what I do is I do the modulus of this. So the modulus of this is as follows. I'm not going to plug into my calculator the truncated values, but just simply for presentation, I'll do this. Okay. Okay, so while I'm writing this, my calculator understands that I have kept all decimal places. So to full precision, a calculation to full precision then gives you this. Let's just see. Okay, so I have this. Okay, now it shouldn't be much more than actually 22.981. Why? Well, because if you look at these components, this is the most dominant term by several orders of magnitude. And this is, when you square it, this is quite small, this second term. So actually, when I do this in the calculator, what I end up with is the following for the speed, 22.984. Now, again, if you're trying to repeat my calculation, and what you're doing is you're looking at the truncated values, and you see that when you pop the truncated values into the calculator, you don't get this answer. It's because you've used the truncated values and you've generated an error. And this error accumulates in subsequent steps. However, if I'm working to full precision and I retain all the decimal places, this is the answer. Okay, so the speed of the ball is 22.984 meters per second to 3 decimal places. So once you've got the answer that's requested of you, you can then truncate. But remember, it's always best to do, if you're going to use this value later on, to use full precision in your calculations. Okie doke, so we need to find the maximum height next, max height reached by the ball. So for this, well, we have the formula just there. It's u square sine square alpha over 2g. All right, so, well, what are we waiting for? It is now, I don't need to bother about any particular time t. I just have to sub the values in and evaluate the result. So I have what? 30 squared sine square of my radian angle, 2 pi over 9, divided by 2 times 9.81. Okay, so if I just plug this in, let me just type this in. So I had 30 square. Again, everything in this formula is exact, which is nice. Okay, 2 times 9.81. Okay, and what you end up with is the maximum height reached is 18.953 meters to 2 decimal places. And really, it's that simple doing these examples when you have the final results. Of course, when you get assignments, I'll be expecting you to model the scenario from scratch and before you start applying them like we have. Okay, so that's all for now.